Hey guys, so I'm going to be delivering your notes to you through these videos, asking that you follow along, take these notes on your own guided notes sheet, which you have a physical copy of. And then I'm going to do a couple practice problems at the end of this video that will help prepare you for the types of problems that you're going to be asked to do in your homework. And on your homework, you're going to use the textbook, you're going to do it on a separate sheet of paper, and you're going to turn that in on paper, all right? And we'll talk about whether or not you're going to do that digitally or just leave the piece of paper with a substitute or how that's going to work. But what we're going to be doing here is just the notes that we would be doing in class together, and it's your responsibility to take down this information and use it to help you, okay? So at the end of each unit, or at the beginning of each unit rather, you're going to see basically just some terminology introduced to you, some simple concepts. We're starting with probability, so we're going to talk about some vocabulary that's important, some notation that's important, and we'll do some probability calculations in this lesson, but they're not going to be super advanced. They're going to be some simpler calculations, things that you've probably done in the past. And initially, what I want to start with is just the idea of the different types of probabilities that we may investigate. So if you were to actually calculate the probability of something happening in practice, we would call that an empirical probability. For example, if I want to know how likely I am to flip heads on a coin, and I flip the coin 10 times, I might get 8 heads, so I would say that my empirical probability was 8 out of 10. But we know that this isn't likely to happen, because if the coin is fair, then you're likely to get heads half the time. And that would be what a theoretical probability is. So the difference there is an empirical probability is the actual probability that was the result of completing an experiment. The theoretical probability is what should happen before you complete the experiment. It's like a prediction of what would happen if you completed the experiment 1,000,000 times. We don't care as much about empirical probability here because we're not going to physically do a lot of these experiments to see what the probability ends up truly being. We're going to discuss what the probability should be, which is theoretical probability. So important to note the difference between these two things. So when I ask for the probability of some event taking place, we're talking about the theoretical probability that that event would take place. Obviously with the understanding that if we were to run the experiment, that may or may not happen. There's a chance that you would get way more heads than you should, or the chance that you would spin way more blues on some spinner than you should. But we want to discuss what really should happen theoretically. Okay, so there's a simple formula that is pretty straightforward. It's very intuitive, and if we want to calculate the probability of any individual thing happening, we would say that the probability of some event taking place. Now this is just notation. If I wanted to know the probability that I flip heads, I might say, what is the probability that I flip heads? And then I would write that probability. This is just specifically saying P of some event. The probability of some event happening is the number of times that event takes place divided by the number of elements in what we call the sample space. So the probability of flipping heads would be saying, okay, well, what is the number of ways that you can flip heads? Well, you could flip heads only one way. When you flip a coin, there's only one way you could flip heads. And how many things could happen? Which is to say, what's the number of elements in the sample space? Well, 2 things could happen when you flip the coin. You could flip heads or you could flip tails. So the number of elements in the sample space is 2, and the number of elements in set E is 1. So again, this says the probability of event E occurring is the number of elements in set E, or the number of ways to get what we want, divided by the number of elements in the sample space, or in other words, the number of possible outcomes. So visually what we've got going on here is a lot of things that could happen. For example, let's say there were a lot more elements in a sample space, and I don't know, we're picking people out of a crowd, and there are 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say there are 10 people in this crowd. This represents the sample space. That's all of the people in the crowd. But if we wanted to know the probability of picking people from this crowd, say, that have brown hair, well, we might say here are the people in that sample space that meet that criteria. So we might say here, the probability of people in the sample space with trait E, maybe it's brown hair, maybe it's green shoes, whatever you're looking at, is the number of people in set E, in this case 3 people, divided by the number of people in the sample space, in this case 10 people, so 3/10 here. All right, it's another just simple example of how this notation is used. And right now it is just kind of all about notation. So if we focus on the next example here, we've got a fair 6-sided die being rolled. It's just like dice that would come in a board game. And we're asked to just list the elements that comprise the sample space. And again, the sample space is just the number of things that could happen. When you roll a 6-sided die, what are all the things that could happen? Well, you could get a 1, you could get a 2, you could get a 3, you could get a 4, you could get a 5, or you could get a 6, and all of these things are equally likely. So if we're to do any investigation at all regarding this sample space, we need to know what are the elements in the sample space. These are the elements in it, and there are 6 such elements. Now we can answer questions like A, what's the probability of rolling a 4? Notation-wise, here's how we would write that. The probability of rolling a 4. 4 is the event that we're talking about. So the question is, how many ways are there to roll a 4? Well, there's only one 4 on this 6-sided die. So there's only one way to roll a 4. How many possible outcomes are there in the sample space? Well, there are 6 possible outcomes. So the probability of rolling a 4 is 1/6. We're not going to turn this into a percent because we're going to run into situations where the percentages need to be rounded, and there's no sense in doing that if we can just go with an absolutely accurate improper fraction. That's the way we're going to leave these. Fully reduced, if we can. B, what is the probability of rolling a prime number? Well, to answer this question, I think we need to think about what are the prime numbers, just kind of off to the side. Prime numbers are numbers whose factors are just 1 and themselves, which means 1 is out, actually, because 1 is itself. So we don't include 1 in the set of prime numbers. 2 is the first prime number. 3 also, its only factors are 3 and 1. 4 is out because 2 is a factor of 4. But 5 is prime. 6 is not. 6 is composite. You could go with 3 and 2. These are all of the prime numbers within the sample space. So when we investigate the probability of rolling a prime number, we would say how many prime numbers exist in the sample space? 3, right? 2, 3, and 5. These are all the prime numbers in the sample space. How many total elements are there in the sample space? Well, there are still 6 because we're still talking about a 6-sided die, the same one. So in this case, we would say the probability is 1/2 because we need to reduce this if we can. Don't forget to reduce these numbers if possible. All right. All right, so now we'll get into just some slightly more thought-provoking probability questions. And we're going to be talking about a deck of cards here. So a card is pulled from a standard deck of cards. You do need to know all of the cards in a standard deck of cards. So I'm going to provide that. I'll post an image of a deck of cards on Google Classroom for you to reference. But hopefully you already know that there are 52 cards in this sample space. So when we talk about a deck of cards, that just means there are 52 cards in a deck of cards. We're not counting the jokers. So to know that there are 52 cards is important because that gives me the number of elements in the sample space, which tells me the denominator in each of my probability calculations here. So A, what is the probability that the card selected is a king? Well, just to remind you of the elements in this sample space that meet that criteria, let's talk about all of the kings that exist in a standard deck of cards. You've got the king of hearts. You've got a king of spades. You've got a king of diamonds. And you've got a king of clubs. Those are all the kings that exist in a deck of cards. So when I say what is the probability of pulling a king from this deck, well, how many kings are there? There are 4. How many elements are there in the sample space? There are 52 cards in this deck. I do need to reduce this if I can. 4 over 52 can be reduced to 1 over 13. So if you were to pull a random card from any shuffled fair deck of cards, you'd have a 1 out of 13 chance of pulling a king. not great odds. And B, what is the probability that the card selected is numbered? Now, I'm not going to list every single card in a deck of cards that would have a number on it, but when we talk about the numbers that show up on any cards, you've got twos, because there is no one card. The ace is the one card, but it's not numbered. Threes, 4, 5, 6, 7, 8, 9, and 10. There's no 11 card, there's no 12 card, there are face cards for those. Now remember, there's a 2 through 10 of each suit. So you see 9 numbers here, but there's one of those numbers for hearts, for spades, for diamonds, and for clubs. So when we say what's the probability of getting a numbered card, the number of elements in that sample space is 9 numbers times the number of suits. So 36 cards in the deck are numbered, because you got a 10 of spades, a 10 of clubs, a 10 of hearts, and a 10 of diamonds, and then you have the same for 9s, 8s, 7s, all the way down to 2. And the number of elements in the sample space is still 52. We need to reduce this, if at all possible. Common factors of 36 and 52 are 4, so we have 9/13. Pretty good odds, if you were to pull a card from a deck of cards, that you would get something with a number. So those are the notes. Now I'm going to flip this over to the back. We'll do a couple practice problems. I would encourage you to do all of the practice problems and to check your answers, which I will post on the Course Notes Hub for you to see. So what we'll do here is we'll do one question from each level, and then I think it would be a good idea for you to finish the rest of the questions in each level. The level 1 questions are going to be really straightforward. Level 2 will think a little bit harder. Level 3 will be challenging and often involve some algebra and some prior skills. So let's take a look at level 1, and we'll do the second question here. So a jar containing 5 marbles has 2 black marbles, and the rest are white. In selecting a marble without looking, find the probability of pulling a black marble. So if we want to know the probability of a black marble, the first question is, how many black marbles are there? Well, it tells us there are 2 black marbles. So there are 2 marbles in this jar that are black, and the rest are white. Now they told us that the jar contains 5 marbles, so that's the number of elements in the sample space. The probability then of pulling a black marble is 2/5. And we don't want to turn that into a percentage. You could call it 40% and it would be exactly correct, but we're not going to do that right now. We're just going to leave these as reduced improper fractions. All right, let's take a look at level 2. Let's do number 1. A spinner containing equally sized numbers 1 through 7 is spun once. So just to give you a picture of what this is, it's like some sort of board game, right? And you've got 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Yeah, they're not perfectly equal here, but let's pretend they were. And you have to spin some sort of arrow, and it's going to land on one of these numbers. Calculate the probability that the number lands on a value greater than or equal to 3. So probability of a number that's greater than or equal to 3. Well, how many elements in this set are greater than or equal to 3? Well, you got 3, 4, 5, 6, and 7. All right, so 5 ways to spin a number greater than or equal to 3. And what's the number of elements in the sample space? Well, that's 7, because there are 7 numbers on the spinner. So here we would say the probability that the number you spin is greater than or equal to 3 is 5/7. All right, and now level 3. So we're going to need to think here. A bag contains 20 marbles, and the probability of drawing a green marble is 2/5. So I'm just going to make note of that. The probability of a green marble being drawn, they've told us already, is 2/5. And they know that the bag contains 12 marbles. So when I set this up earlier, and I said the probability of any event taking place is the number of ways to get the desired outcome divided by the number of elements in the sample space, that's 20. So that means this must be a reduced value, because there are 20 marbles in the bag, but the probability of pulling a green marble is 2/5. So then the question is, how many green marbles are in the bag? So really what we'd like to know is that. Well, I know two things. I know that the probability of pulling a green marble is equal to that. And I know that the probability of pulling a green marble is equal to this. So let's solve for the number of green marbles in the bag. To do that, I'm going to want to isolate the number of green marbles. So I'm going to multiply by 20 on both sides. And when I do that on the left, that's 20 times 2. And now I have the number of green marbles, because 40 divided by 5 is 8. So there must be 8 green marbles in the bag.